Okay, chapter 7 is called ionic bonding. So we'll be learning about ionic compounds and how to create them, as well as how to name them. So the first section, which is 7.1 in regular and pre-AP chemistry, is called ion formation. The main point here is for you to understand how to create an ion. And as the main idea says here, ions are formed when atoms are gaining or losing valence electrons. This is different than sharing electrons. When we talked about sharing, which was covalent bonding, the atoms will have a partial charge because they don't completely lose or completely gain electrons. They just share them. In ionic bonding, we're talking about a full, complete transfer. So I'm going to 100% lose my electrons, or I will 100% gain them. So I will gain an extremely strong 100% positive or negative charge. So this section will discuss how to make that happen. As a matter of fact, the 3 questions you want to focus on is first, how do we create these positive and negative ions, as we call them? Secondly, how does ion formation relate to the electron configuration of the atom? And then lastly, what is holding the atoms together in a chemical bond? So first, let's talk about how do we create those ions. We talked about what's called noble gas configuration, electron configuration. If you look at chlorine here, you have its electron configuration down here. The outermost level for chlorine is 3s2, 3p5. So there's 1, 2, 3, 4, 5, 6, 7 valence electrons. Chlorine has a tendency to gain 1 more electron. So not only does the size of chlorine increase when that happens, but the electron configuration also changes from 3p5 to 3p6, which is also the exact same electron configuration as argon, a noble gas. The question is why? Why are atoms doing this? Why is chlorine doing this? As well as a side question, what causes the size of chlorine to increase? And as you may recall from periodic trends, more electrons mean more electron repulsion in the cloud. So that makes the size larger. So how and why are these ions forming? That's because they're going to follow what's called the octet rule, which means all atoms want to have 8 valence electrons. That would be stability, happiness, the lowest energy, the most stable state of an atom. So you're either going to gain, lose, or share electrons to make that happen. Now, if you're sharing, we call that covalent, and that is a whole different chapter, as we've already discussed. But if you're not sharing, if you're going to steal electrons or give them away, we call that ionic bonding. Now, when you look at the periodic table, we can look at a lot of different patterns and trends. One thing that we notice is that nonmetals are on the right side of the periodic table, and they tend to have the highest number of valence electrons. The more valence electrons you have, the higher your tendency to hold on to them, and even still more. Because you have like 4 or 5 or 6 or 7, you're really close to having 8. Versus an element that has only 1, 2, or 3. Then you're just going to try to get rid of your 1, 2, or 3 so that the inner shells can be now the new outer shell. So in general, nonmetals will gain valence electrons to fill that shell and become negative, because if you are gaining negative electrons, you're adding something negative to yourself, it will make you negative. And the reason being, of course, is because you'll have more electrons than you do protons now. The opposite is the case for metals. Metals will lose their valence electrons and become positive. And if you have less electrons now, then you're going to be more positive. You've gotten rid of things that were negative. That should make you more positive. Here are 4 examples of ions. You have the chloride anion. We have the sodium cation. We have an aluminum +3 cation, and we have a nitride anion, and we'll learn about the names in the next section. But we see here that says chlorine -1. So it somehow has went through some type of change to become a -1 charge. Same thing with sodium, except that it became positively 1 charge. Aluminum +3, nitrogen -3. So let's look at the case for sodium. Here is the Bohr model for sodium. It has 11 protons and 11 electrons, which means it is neutral. 11 positives and 11 negatives cancel out. If you draw the Bohr model correctly, you'll have 2 in the first ring, 8 in the next ring, and then there's 1 left over in its valence shell. It wants to be stable and follow the octet rule, so that means it will try to get the outer shell to have 8. Well, what should it do? If it has 1 in the outer shell, should it gain 7? Or can it just simply get rid of the 1 and now the outer shell will be the second level? Well, that's exactly what sodium would rather do. Get rid of that 1 electron, and now the second level that was full will be the new outer shell. And that is what will cause sodium to be stable and happy. So by getting rid of 1 electron, you now have 11 protons still, but only 10 electrons left, which gives you a positive 1 charge now. In other words, you lose 1 electron, you become positive 1 charge. The same thing would happen for aluminum, but notice that aluminum has 3 valence electrons. So what do you think would happen to aluminum? It's going to lose those 3 valence electrons so that the new outer shell would have 8, which would be the second level. A good question is, what happens to electron configuration as a part of that process? If aluminum loses the 3 electrons it has in the outer shell, that outer shell completely disappears. If you look at the electron configuration, here are the 3 electrons, that third level 3s2, 3p1. If they go away, those 3, it'll have the electron configuration 1s2, 2s2, 2p6. Which noble gas is that? I'm pretty sure you can see that on the periodic table. If you lose 3 electrons, aluminum plus 3. What about fluorine? You have a regular fluorine atom here, which has 9 protons and 9 electrons. Fluorine has 7 of those electrons in its outer shell. If it had only 1 more, it would have a full outer shell. So if it does gain that 1 electron, it will now have a negative 1 charge. And the name actually will change for fluorine to fluoride, the fluoride anion, as we'll discuss a little bit later. Okay? What would happen for chlorine? Chlorine has 17 electrons, but just like fluorine, 7 of them are on the outside ring. So what would chlorine like to do here? Of course, gain 1 more electron. And if it does, it will now have a negative 1 charge. And notice the way that they have written the electron configuration here, you see that it used to have 7 and now it has 8, but picking up 1 more electron now produced a negative charge on chlorine. And the name for chlorine, just like fluorine became fluoride, chlorine becomes chloride, the chloride anion. So in general, when you're forming an ion, if you have a positive charge, we actually call that specifically a cation ion. Some people like to say cation, and that's not correct. This is a cat meow meow ion, cation. Sodium, once it has gained some energy, that outermost electron will pop off. When that electron pops off, it's now away from the atom, and the sodium is left behind with a positive 1 charge. All right. Remember, we used to call that energy required to remove an electron ionization energy, or some people call it binding energy. How much energy does it take to make that electron go far away from the atom? Most metals will be losing their valence electrons. Well, pretty much all of them will be losing their valence electrons. The group 1 metals, it's very easy for them to go through the process because they only need to lose 1, so it's easy to lose 1. Most of them in group 1, all of them in group 1 will be losing 1 electron, and as a result of the process, their electron configuration will change. They will gain a +1 charge. Everybody in group 2 will end up losing 2 valence electrons and become positively 2 charged. Everybody in group 13, which is also known as 3A, will lose 3 valence electrons and gain a positive 3 charge. What is the relationship between your group number, how many valence electrons you have, and the ionic charge you have in the end? Now for the transition metals, which are in the middle of the periodic table, there is no pattern for knowing which one will do which unless you just straight up memorize it. Okay, you have copper, gold, zinc, silver, platinum. All of these guys, they don't have a pattern like the regular representative elements in group 1A, 2A, 3A, 4A. It's whatever group number you're in, that's how many valence electrons you have, and it's easy to predict the charge. But the transition metals, however, they're scattered all over and it's kind of random almost. So really the only thing you can do is make flashcards to memorize them, but there are tricks that I'll teach you in 7.2 to help with that. But here's an example of a transition metal zinc doing the same thing as sodium. Zinc's electron configuration, you have Ar4s2 3d10. Just because we wrote 3d last does not mean that 3d is the outermost shell. It's whatever the highest energy level is. That's the outermost shell, as we discussed before. So that would be 4s. 4s is the valence shell. And you see there's only 2 electrons there. So zinc is going to lose those 2 electrons. And when the 4s2 electrons disappear, 4s disappears completely. So you only have 3d left, of course. So here's the new electron configuration. And if you lose 2 electrons, you gain a positive 2 charge. The 2 electrons have left the building, leaving zinc behind with a positive 2 charge. Okay, so zinc and the rest of the transition metals will become positive. It's just that it's kind of harder to figure out what charge it will have. And they're called transition metals because a lot of the metals have different numbers of valence electrons at any time. Like copper can be +2, copper can be +3. That means copper can have 2 valence electrons, and then one of the inner electrons could go to the outer level, and now it can have 3 valence electrons. The electrons can transition back and forth between the energy levels. So the only way you can know what's going on with copper, well, we'll actually talk about that in the next section. What about the nonmetals? If you have a negative charge, we call you an anion. I like to go ahead and mention the shortcut for memorizing what the word cation means versus anion. I tell people when you write out the word cation, I'm using a mouse to write the word cation. That's kind of, is that a pun? Or I don't know what that is. Anyway, the T in cation is like a plus sign. So that's how you can remember that cations are positive. And then when it comes to the word anion, the N in anion reminds you of the word negative. Okay, so that's how you can remember which is which. And anion is negative. We know that nonmetals will want, just like the regular metals, they all want to have 8 valence electrons, but the nonmetals, they will tend to gain electrons to get to 8. Okay, and we know sulfur and phosphorus, as we mentioned before, can break the rule, but look at chlorine. Chlorine will have 7 valence electrons, so it's going to gain 1 to have a total of 8 valence electrons, but in the process, it will have a negative charge. This picture is just telling you that it's actually going to release some energy to make that happen. You got to take in energy to make the electrons get excited, and they will leave. To bring electrons in, it seems that chlorine will lose energy in that process. We'll talk more about that when we get to another chapter called thermo. But in general, if you look at the nonmetals in group 5A, group 6A, and group 7A, you have 5 valence electrons, 6 valence electrons, 7 valence electrons. If you have 5, you're going to gain 3 to get to 8. If you have 6, you're going to gain 2 to get to 8. If you have 7, you're going to gain 1. So then your charges will be -3, -2, -1, respectively. As a matter of fact, the shortcut that I tell people to write on their periodic table is everybody in group 1 has 1 valence electron. So they're all metals. They will lose that 1 to get a +1 charge. Group 2, everyone has 2. They're all metals, so they'll lose those 2. And when you lose 2 valence electrons, you become positively 2 charged. Group 3, if you're losing 3, your ionic charge will be +3. If you are in group 4 and you are a metal losing 4 electrons, then you will be +4. Now, there are nonmetals also in group 4, so they're not going to lose 4, but they will gain 4 electrons. So that means if you're in group 4, you can either be positive or -4. It just depends on if you're a metal or a nonmetal in that group. Group 5, same thing. You're going to be gaining 3 for the nonmetals, however. So if I add 3 electrons to myself, I become -3. Look at the pattern. Look at group 8. They have 8. So will they lose any? No. Will they gain any? No. So they will have no charge. You will not see them with a charge at all. All right? +1, +2, +3, plus or minus 4, -3, -2, -1. Make sure you write that on your periodic table. So here is just something you can practice on your own to get the hang of predicting the charges. Beryllium is in group 2. So that means it's going to be +2. Oxygen is in group 6. Everybody in group 6 will be -2. Lithium is in group 1. +1. You can go through and do them for all of them. Okay? Hydrogen as a cation. So hydrogen is not a metal. It's actually a nonmetal. But it is in group 1. As we've discussed, it follows the duet rule. So either it's going to gain 1 electron, but it has the option of losing an electron as well. So the question here is, what charge will hydrogen have if it acts like a cation? And then what charge would hydrogen have if it acts like an anion? So what will happen to H if it loses an electron? And what will happen to H if it gains an electron? Why are the atoms, well, now they're ions because they have charges, why are they flying towards that special group outside the window? This guy has no charge. Why isn't he flying out? Well, a chemical bond is a force of attraction between 2 atoms. There are different types of bonds. We talked about covalent bonds, which is a force of attraction caused by sharing electrons. But in this chapter, we're talking about ionic bonds. And that would be a force of attraction holding ions together. And you're making those ions by transferring electrons between atoms. Take a look here at sodium and chlorine. Sodium has 1 valence electron and it would like to lose it to become stable. Chlorine has 7 and it would like to gain 1 to become stable. So if sodium transfers that 1 electron to chlorine, sodium will become the sodium +1 cation, and chlorine will become the Cl-1 anion. That positive charge will be attracted to the negative charge, and that will make the 2 ions stick extremely close to each other. And sticking close together, that attraction is what we call the ionic bond. And when you put those 2 elements together, and you put those 2 ions together rather, they form what's called an ionic compound. So that's 2 or more atoms bonded together through an ionic bond. We call that an ionic compound. As we'll learn in 7.2, we can actually name that union, that attraction, that relationship. We can name it between sodium and chlorine. We call that sodium chloride, table salt. And if you don't want to write the name, we can write the formula NaCl, and we'll learn that in 7.2. All right, so that's the end of 7.1. Please work on the assignment for 7.1, which is just going to test you over predicting the charges, the number of valence electrons and the charges for the different ions, and basically how those ions are being created.